Right. So welcome back everyone to lab session number 4 on image segmentation. So let's before starting, let's actually do a small recap of what we've done till now. We were on lab 3 and we started with computer vision. We started learning about convolutional neural networks, for example. We trained a convolutional neural network and we also learned how to build some advanced architectures such as the ResNet architecture and whatnot. So we've done that, and we also learned how to train those using our existing API that we created, which included the optimizer, loss functions, and etc. etc. Let's come to a very specific problem in computer vision, which is known as image segmentation. Uh, it is one of the most famous problems that exists, and let me just show you what exactly that means. So till now we've seen classification of images, like say for example cats versus dogs. So you classify it as a 1 or 0, cat or a dog, something like that. A classification problem in such, like in the output, the type of output is completely different, and it comes used to us in many different ways, as you see. Here is an example of what segmentation looks like. I have an image of a random street. Some people crossing the road. There are cars. There's a pillar. There's a road. There's a zebra crossing as such. And I would like my neural network model, my AI model, to tell me which pixel corresponds to which object. So which pixel corresponds to this person over here, which is colored green? Which pixel corresponds to a car, which is given by the color red? Right. Another example is over here. So I think all trees are given the color green. All people are given the color red. Every road, the pixels of the road are given the color purple. Cars are blue. Buildings are grayish, and so on and so forth. So this is what you call image segmentation. Now, if you think about it, this is essentially a classification problem. You're going over every pixel in the entire image, and you're doing this sort of spatial analysis to understand. You're telling the neural network model to learn which pixel do you think that this, so which object do you think this pixel belongs to? Is this pixel part of that person, or is that pixel part of, let's say, the road or the cars or something like that? And based on that, you're going to ask the model to classify which object do you think the pixel belongs to, and based on that, you get these color codings and stuff like that. So that is what that is what is known as image segmentation. It also has some other names. It's known as pixel level image segmentation and stuff like that. And it was first introduced in 2015 in this paper in a biomedical conference known as Convolutional Networks for Biomedical Image Segmentation. Anyways, the problem was essentially segmentation of certain neuronal structures, and this architecture no one had ever seen before, and it's still used till date. I mean, it became so famous. So I mean, this is one of the examples of those architectures which has, in fact, stood the test of time. And let's actually see what kind of architecture we're going to be dealing with. This is the kind of architecture we're going to be dealing with. It looks like a U, if you think about it, in its pictorial representation, and that is why this architecture is called as the U-net architecture. U network, right? Let me just, it might look actually confusing. Let me just get this very clear. That let me break this down into two parts, right? Let me break this down into two parts right in the middle over here. And this part that you see over here is nothing but the standard classification neural network model that we've already built. Standard convolutional neural network. So it takes in a certain number of channels, gives out like more 64 number of channels. 64 number of channels become 128. 128 becomes 256 channels. 256 becomes 512. 512 becomes 1024. So that's how convolutional neural networks go ahead, right? This is essentially just that, nothing different, right? But you see what happens with a standard convolutional neural network model. It only gives you certain feature values, right, which can be used to predict like which class something belongs to. But over here, what you essentially want is a picture as an output, right? So if you give an image, this image, for example, you want another image which tells you which pixel belongs to which class, right? And that itself is going to be an image on its own. So in computer vision lingo, it's called a mask, a segmentation mask, which contains color codes or like numerical codes for each of the given pixels based on which category they belong to. So our model takes in an input and does our standard convolution neural network stuff. But we need to do something before we can before we can get segmentation masks or images themselves as outputs. Which is why someone devised a plan that said that, well, let's do an opposite of a convolution neural network model, standard convolution neural network model that takes in features over here and gives out outputs over here. Gives out a standard image. So a standard convolution neural network model takes in an image, gives out features or like certain neuronal what do you call activations. This thing that is the opposite of a convolution neural network model takes in certain features and gives out an image, and that is known as okay. So there is a certain language for this. This is called the encoder, right? This part is called the encoder. Sorry for my writing, I don't have a pen. Encoder, and this part is known as a decoder, which is the opposite of a standard neural network model. So we learn how to build this. So let's actually get started with the code, and let's first set up our data and let us set our data sets, and then we'll come on how to build this data set. We'll be implementing this paper, which is I'll send the link on the chat box, by the way. You guys can have a read. This is the original unit architecture paper, and we'll be implementing this paper from scratch. So quite an interesting class. All right, so let's actually first build our data sets. And then once we're done with that, once we're done with our basic setup, we'll start with building the model actually. You guys can follow me. Let me just share the link to this notebook really quick. And you guys can code along with me. I'm going to be coding everything. Right, so I'm sharing the link on the chat box. You guys can have a look. All right, let's start by importing some libraries that we're going to use. We're going to be using PyTorch as always. So there's Torch. We are building neural network libraries, neural network models. So we need this torch.nn. So I'm going to be importing that from Torch. Import nn. If you remember that we applied certain transforms onto our data, which is always necessary, and those were available in the Torch Vision library, which is the computer vision library from PyTorch. I would need that. I mean, I just have a basic idea that I may or may not need them. If I don't need them, I'll just delete them later on, right? We're going to be dealing with images, and for dealing with images, we need a library that can handle that. So there's PIL, which is the Python image library. We need that. We're going to be downloading a data set. So we're going to, if you want to iterate through data sets that is available on the hard drive of this Google Colab, you'll need two libraries. One is OS, which you'll need to iterate through all those directories and find all those images. And because computers don't understand strings by themselves, you need a certain object which is of the type path, which explicitly is designed to handle directory paths and so on and so forth. So there's that. So I'm going to be importing OS. I'm going to be importing the path library, the path module from the pathlib library. So I think this is enough for now, and whatever we need, we'll just keep on importing that. All right, so I'm going to be using something known as the portraits data set. Yeah, it contains about 15,000 images of portraits, and your task is to find out which pixel belongs to the face and which pixel belongs to the background. So it's essentially a binary classification problem. 1 may correspond to the face, 0 might correspond to the background. Here's what it looks like. Any example? Yeah. So there's a face, and the black pixels over here correspond to 0, and anything which is a face should be identified by the model as 1, and that is what we're doing over here. All right, so I couldn't find a very good format for this data set, so I've already saved it in a Google Drive. And I'm going to send the link over here on the chat box, and I'm going to type it over here as well. And what you're going to do is we're going to directly download it from Google from Google Drive. And I'm going to link to the data set. Right. All right, so first I'm just going to save it as a string. So this is, by the way, I'm going to save it in a variable known as file, and I'm going to be using something known as the gdown library, which is actually a library specifically designed to download things from Google Drive. So Google download, gdown. And this is not going to be run through Python. It's actually going to be run by Linux, right? Because you're going to be downloading everything to the Linux subsystem on which the Google Colab is running. So I'm going to be downloading the file over here, and let me just see if it works. Oh, before anything starts, we're going to be needing the GPU later on for running this code, because I mean, once you actually enter like really large models, it becomes really infeasible to download them, to train them on the CPU itself, and you need the GPU in order to accelerate your training, to actually train your model in a reasonable amount of time. All right, so I have something known as the portrait.zip file. We'll convert it into a, all right, let's do this. Before you start, sorry for this, let's change our runtime to a GPU. I may be on a, I've run out of my GPU usage units. So let me just share it with my other account, my personal account, and we will run it from there. Yeah. So I'll go to runtime, I'll change my runtime to a GPU, my hardware accelerator to a GPU. And I'll have to run everything again from scratch because so it's about 107 MB, and we'll see. And we have something known as the portrait.zip file. I'm going to be importing a library which is designed to extract files from zip files. So it's known as the zip file library. And there's this module known as zip file with a capital Z and a capital F. Make sure of that. Very sure it's this. And let's extract our files within this portrait.zip file. So our folder that we need to extract is portrait.zip. Right? And I need to read this file. So you need to specify a mode in which you need to open it. So there's a read-only mode, there's a write-only mode, there's a read and write. Over right now, we don't actually need to write on it because we're not editing the data set in any ways. We only need to read it. So we're going to have to open it in the R mode, that is read mode. Right? Standard stuff, nothing special. Right. And I'm just going to do some ref dot extract all in the same directory, like wherever you want to extract. All right, let's see. Yeah, we have certain files over here. There is a text file which is for training and validation, which may suggest like which images you want to use for training and which you want to use for validation. But it doesn't really matter for us. We'll just simply do a 80-20 random split. The images, the ground truth, I'm sorry, the actual images are saved within this folder known as images data crop. And the ground truths or the labels or the segmentation mask, which is which is how we're going to tell the neural network model to identify which pixel belongs to which class. And so it's essentially a supervised learning problem. Is present in this folder known as GTPNG, which stands for ground truth in the PNG format. Something like that. All right, that's that. So now I'm going to be writing some code to first of all extract my data set, and so the first step we want to do is to first identify the paths of all the images within your within these directories. So I'm not going to. So if you remember last time we wrote this simple piece of code. Yeah, this kind of for loop system that goes on and on. I now realize that I will have to do this for my x's and my y's as well, because my y's are also images now. So I need to like iterate through those directories and find those parts of the images which correspond to the masks themselves. And so I shouldn't have to write anything twice. First rule of coding: don't write anything twice. So for that, I'm going to be actually writing a function which will help me facilitate this process even in further classes and today also. So I'm going to be naming this get images. That makes sense. I'm going to take a path, and optionally maybe it's going to take like what extensions are acceptable to you. So for example, if you're extracting images can be JPG or PNG. I'm not sure which is which. So I mean, like if there are only PNG images or JPGs, I'm just gonna write both. That's okay. Just a mistake. Don't think so. Anyways. Okay, anyways. We'll see. Or let me make this slightly more flexible and not write it over here. Let's save it in a variable known as image extensions. All right. Let me just name image extension over here. And now the task of this function is to go through all the directories that exist within a data set, or whichever we specify, which in this case are only these two directories over here, GTPNG and images data crop, and find all those paths of files that end with either JPG or PNG. So either of both will work. All right. So all right, let's just do. So just for flexibility purposes, the user can pass either a string or a path object, which we've discussed before. But like even if the user passes a string, it should first be converted into a path object, because computers don't understand strings as directory paths. So we need to first convert it into a path. Nothing special. And all right, so I'm going to be creating a list of all the paths of all the images that exist within my directory. So all right, and this is a standard piece of code that I wrote over here. Let me just copy paste this. All right. right? That's done. But I don't need this y over here because this can be run independently for both x and y. So the same principles apply. So there's just x over here. And finally, I'm going to be returning x, right? But what about, so the last time we actually assumed that all the images will be JPG. We're now trying to expand. We're trying to make our API slightly more flexible. So I'm going to be writing a function that will return true if the image file ends with either of the extensions that you've allowed, which is JPG or PNG. Now, images are actually can be of many different types of formats. There are some 30, 35 different formats, including PAT or different kinds of formats. You can find you can Google search like what are different kinds of image extensions exist. Anyways, so I'm going to be defining a function known as ends with. I think that makes more sense. It's going to take file and the whatever extensions that you've allowed. So maybe let's just define this function over here. F ends with, and I'm defining a function within a function. That's totally allowed in Python. And it's going to take extensions. And this is going to be a list, by the way. So I'm just going to specify that for the users. Let me just add a doc string over here. It returns true if file ends with either of the extensions given in the ext list. All right. There's a very clever trick to return true if either of those exist, because you don't want to go, because otherwise it's very cumbersome. Like, what would you essentially do? You would say that you would store that you would do a for loop across all the extensions, and you'll say that, well, does it end with this? No. Does it end with that? No. Does it end with that? Yes. Does it end with that? No. Does it end with that? No. And then finally you're going to do something like an or, which is no or yes or no, and this is going to give you yes, and that's going to be a final answer. But that's very cumbersome. Like, once you find yes as your answer, you should stop, right? There's no point in going across all, because the condition that is specified is that either of those extensions must exist, right? And so you don't need to iterate through all of them. So a very clever trick to do that is to structure your OR conditions within the for loop itself. Like, the for loop itself is the OR condition. Let me show you what that means. So initially, I'm gonna initialize a variable as true. By the way, at the end, I'm gonna return this res, which is either true or false. And I'm gonna say that for O in extension, in the list of extensions, res is equal to res or file dot ends with ext. So what it's going to do is that it's going to go for JPG, and it says true, or let's say the file ends with PNG, for example. So res, which is true, or this is going to be false. So true or false will be true, right? Okay, so it's going to go for the next extension, which is going to be PNG. So it's going to be true or true, which is going to give you true. So finally, the loop ends over there. Now, for example, let's say that it ends with JPG, and you're going to say true or true, which is going to be true. And now when you go for the second one, because res is already true, right? The model simply won't check the second statement. So that's essentially the purpose behind this kind of structure. All right, this is it actually. I think this is enough. This is done. Let's see. So I'm going to be naming a path standard. This is the path where my images actually exist.
Excuse me.
Yeah.
Res should start with false, right? Because otherwise it will always be true.
Yes,
yeah.
Yes.
And for O and EST, so file end with O, right?
You're right.
Okay.
Thanks. Yeah. Anyways, all right, so we have a path now, and that is extract all those file names that we have using this function that we've just created. It's going to be path slash what's the name of the file? Images data crop. And let's see if that works. Root is not defined. So okay, I need to change this. str object has no attribute ends with. All right. So I need to make sure that I'm passing in a path over here. All right. So by the way, I don't need this image.open over here. That must be changed first of all. And yeah, let me just do path. Let's see. Oh, sorry. This must be a string. Sorry. Right. Oh, end with. It's ends with. Maybe I don't like this. The name self is not defined. So yeah, we're not working with classes anymore. So self must be deleted. Yeah, it works. All right. So it's a path object, which is images data crop slash 02087. All right, and it's a JPG file. Now, you see why we needed both JPG and all. Ground truth is in the PNG format, as it's mentioned over here, and images over here are in the JPG format. So you need to be flexible with the API, right? All right. Okay, we have files now. So let's also get labels. So labels names will be also through this function itself, which will be path slash GT PNG. Right. And F names I've already defined. So that's that. Let's go LVL names. Right, I have my images over here and so on. If you really want to visualize how these images look like, let's use the image library that we use, and to open an image using the path of the directory, you're going to be using the image.open function, and you're going to put in a certain function like a what do you call it, path over there. F names. And you're going to get an image. So this is the kind of portrait that we are actually working with. Slightly large in size, but it's okay. We'll reshape it later. So your task is to classify all these pixels on the face and on the t-shirt and on the shoulders as 1, and all the pixels from the background as 0, or the vice versa. It doesn't really matter, right? All right. So this is your images, by the way. These images are by themselves of no use to us because we are like PyTorch only works on tensors, and tensors are going to be the data structures that are actually going to come in handy for us. So anyways, let's just go ahead and we'll think of that, how to do that later on. And now we're actually going to be building the data sets. Just another heads up. Let's actually see what your segmentation masks looks like. Look at this. LVL names 0, I think it will show up. Yeah. So this is By the way, these are not the same person necessarily, because OS doesn't necessarily like order them in any particular way. So it can be of any order, and so we need to mention how to pair inputs and outputs later on using when we're building a data set. So this is what a segmentation mask look like. So this is a one, for example, of these white pixels that you see, and the remaining is in black pixels, right? All right. Let's actually build a data set, right? And if you guys remember what a data set was from our last lab session, you will remember that data set is a class, a Python class, which has three things. Number one, it has the X's and the Y's, right? In whatever format you want. It has a dunder len method, which is going to be telling like how big the data set is, so the length of the data set. And it has a get item, dunder get item, which is basically the method you use for indexing a data set. So when you say data set 0, it should return X and the Y at the 0th index. All right. I'm going to be so the format actually remains the same. I'm going to be needing this. So I'm going to needing the torch.util, so data.dataset and random split. I will also need a data loader, so let's go ahead with that. And what else? Let's actually first copy paste this, and we'll do whatever amendments are needed after that. So let's copy paste that, and let's first of all change this. This is called the segmentation data set now. It's gonna take in. So because now things are slightly different and X's and Y's are present in two different directories, I'll have to specify them separately. So X path, Y path. That's that. Instead of Y path, let's not take Y path actually, because if we do X path and Y path separately, there's no way to telling this code that how to correspond inputs and outputs, because we're going to basically having this problem over here that says that the 0th index of the X's is this image, but the mask at the 0th index is of something else. So we need instead, let's actually define a function that maps an X, whatever X you have, to its corresponding output. So I'm going to be writing Y function rather than the path of the Y itself. All right. Transforms remain the same, but now images themselves, sorry, the Ys itself are images themselves, so they may have transforms of their own. We may or may not need them, but one is for sure that you need to convert them into tensors, right? So you anyway need transforms for Ys also. That's that. And default value is none. All right. Since we don't have explicit classes as of now, I'm going to be removing this line over here. Self.transforms, this is the same, and I'm going to be doing the same for Y transforms as well. This is going to be a lambda Y, if not Y transforms. So these are, by the way, Y transforms. Else Y transforms themselves. All right. Self.x. So initially, the data set should only store the path of the file names. So it's going to be f names is equal to get images from x path. Sorry. Yeah. X path. And self.y f names will be nothing but y function applied to every x for x in self.xf names. So it's so there's this function which is yfn, which we're gonna define later on. It's gonna take in the path of an x and it's gonna give you the corresponding path of the y. So that's how our API is gonna work. This is not needed anymore because we've already defined this within the get images function. Len will have the length of the xf names or yf names. That's both the same. Get item. we'll be applying the transformation to our x, which we did last time, and we're also going to be doing it for y. Self dot y f names. By the way, this is f names. Self dot y transforms. And the applied transforms will be the same as before. I hope this works. Okay, I must have missed yeah, invalid syntax. Oh, okay. Yes. It says the error is over here. So I'm very sure that. Oh. Yeah. Worked. All right. Let me define the data set, which is the segmentation data set. X path is going to be images data crop. Sorry. Y function is going to be. I'm going to defining a lambda function over here, which we learned in the very first lab, which is lab 0. And it's going to return path gt png. By the way, let's look at like what is the format of a particular image of the y category. Let's for example. So for every image that is of 02807.jpg, the mask will be something like 02087, for example, underscore mask.png, and it will be present in the gt.png file. So I'll just format it that way, right? That's quite simple. All right. Path slash x.stem, which will be basically x.stem refers to this part. So this is called the stem, and this is called the suffix of any file path name. It's standard string language, right? So strings are defined this way. I mean, they are. It's a convention, nothing else. X.stem. Sorry, this will be in curly brackets because underscore mask.png. I think this is all. And I'm right. Sorry. All right. And I'm going to be defining my transforms, which is almost the same as before. But first of all, because we only have paths of the data set, first of all, right? Because these x's are not images themselves, they're the paths of images. It's much simpler. It's actually easier for it's much more data efficient, right? Because whenever we are accessing the data set anyways, we're going to be using the dunder get item method. And the dunder get item method has the ability to apply whatever transforms you need. So why save images in the data set class, right? Why not simply save the data, the location of the file, and you can apply the transform. You need to first convert it into an image and then convert it into a tensor. You can do that in the dunder get item method itself. So the first thing that you need to do is to first convert the path of the data set of the file into an image, and that needs to be converted into a tensor. So that's as simple as image.open followed by now if you look at this, and I'm telling you about certain anomaly that I realized while I was designing this lab. These are black and white images, right? So there is this slight probability that some images are actually not three channeled, but they're one channeled, because one channel is enough to make a black and white data set. So I need to make sure that any one channeled image is first converted into a three channeled image, because otherwise it's going to create a problem for my data loader, because data loader cannot stack three channels with one channel. They all need to be of the same shape. So for that, I'm going to be passing it through a function known as it's a method of the image module, which is known as convert, and I'm going to convert it explicitly into three channels of the RGB color type. So I'm just going to write a function, because everything needs to be a function, by the way. Lambda lambda image image dot convert RGB. That's all. All right, that's it. Next is just simple converted into a tensor. Transforms dot to tensor, and like last time, we also need to crop it from the center, because the original images may be very large. Also, it may be possible that certain different images are not of the same shape, so they cannot be concatenated into a data loader. That's also a problem. This is actually not the case in this data set. They've mentioned that these sizes are constant, but we cannot. But models GPUs cannot handle like very large images, so it's always wise to use a smaller shape. Torch vision dot transforms dot center crop, and maybe of the size, let's say 400. Yeah, standard size. Okay, that's done. Now Y transforms also need to be Y transforms is equal to image.open. All right. This doesn't. So by the way, the masks are going to be of only one channel. It's not going to be of three channels, because it's just numerical maps, right? So this pixel is either 0 or 1. 0, 1. So you don't need three channels for that. You just need one channel for that. So I don't need to convert it into an RGB format. And same thing as before, that first convert it to a tensor. And once you've done that, all you need to do is crop, center crop, just like before. So that's that. All right, so I think this is done. And let me just close this, this entire. Let's see if this works. But I think it works. Yeah, it works. So at the 0th element, it will have two items. That is, either the 0th will be the X, and the item at number 1 index will be Y. So at the 0th index, which is X, you have an image of size shape 3, 400, 400. 3 because it has three channels, RGB. 400 because we specified that we want to do a center crop of 400 size. And let me also look at Y. And Y should have one channel ideally, and that is true. It has only one channel, 400, 400, and so on. All right. We've done this. Next step, data loader, right? But now I need to, just like before, I first had to split my data into training and validation data set, and then I created data loader separately out of them. So I'm going to be doing that. I'm just going to be copy pasting that. See. I hope it works. All right, it works. That's done, and training and validation data set. The batch size actually seems very large to me. I don't think the GPU will be able to handle that, because last time we were actually dealing with MNIST data sets and things like that, which are very small images, right? So So, but now actually we're dealing with 400 times 400 pixels. I don't think, and segmentation masks itself are like, so it doubles the size essentially like of any data point. And so the batch size I think should be reduced, but we can adjust that later on, right? All right. While we're at it, let's also define like some CUDA characteristics. So dot device. Zero, which means that the first CUDA core that you find. And torch.CUDA dot is available. So this function will tell you whether or not GPU is actually available, which in our case it is. It's CPU. Device is CUDA. Anyways. Let's also see if our data loaders are working now. So x comma y is equal to next data radial. Let's do x dot shape and let's do y dot shape. Yeah, so 8 images in a batch, 3 channels, 400 times 400. Y will be 8 images in a batch, 1 channel, 400 comma 400. Such. All right, so now let's come to the segmentation model itself, and now comes the fun part where we'll be implementing the paper from scratch. All right. Implementing the unit architecture from scratch. Let me just paste the link. And yeah, I've put it on the chat box as well, so you guys can. I had put it on earlier on. So let's understand how this architecture works. Hey, remove all of this. Right. Okay. So the unit architecture consists of 2 parts, as you talked about, the encoder and the decoder. The encoder is a standard convolution neural network. It takes in an image, gives out features. Now, and let's actually also be slightly more deductive about this. It takes in an image, it does a convolutional it does 2 standard convolution operations, which will give you 64 channels and 500 something pixels. That needs to be that follows by a max pool, which is with a stride of 2, with a 2 by 2 let's say kernel size, which will essentially find out. So what is max pool? I don't know if I've showed you guys, but let's see. Max pool essentially means that you iterate through all the pixels in groups of whatever kernel size you choose, which in this case is 2 by 2, meaning a grid of 4 pixels, 2 height, 2 width, and it's gonna return the maximum value that exists in all those 4 pixels, and that's going to be one value that you get. Now, what happens because of that is out of every 4 pixels, only 1 pixel remains. So for one axis, out of 2 pixels, 1 pixel is chosen. Out of the vertical axis, also out of 2 pixels, 1 pixel is chosen. So you're reducing the height and the width by 2 because of that. And that's what essentially happens over here, where 568 by 568 height and width is reduced to 284 and 284. And when you're actually reducing the width, the height of an image, you also need to double the number of channels. So 64 becomes 128, 120 becomes 256, while you're reducing the height and the width. Until you come at this final point where you have a certain number of height and width, and you have 1024 channels. This is, by the way, the original unit architecture, and you can of course modify this, but for now we're going to be sticking to this. What happens now in the opposite of a convolutional neural network, which is known as deconvolutional network. So the opposite of convolutional network is deconvolution. It's also called the decoder. So this part is called the encoder, which is a standard neural network. The opposite is called the decoder. What they do is they do something known as up convolution, which is given by this green arrow over here, which is nothing but conv transpose 2D. So conv transpose 2D in PyTorch implements this up convolution. The way it works is that what it will do is that instead of let me show you a visualization actually. I may have created it. So I created this visualization last semester for another class. But let's see, I think it was true. So this is the unit architecture. And what it essentially does is that it first breaks apart the entire picture by breaking them apart and filling the spaces in between with blank pixels, 0 pixels. So first you're expanding the size of the image by twice in both dimensions, so 4 times, it becomes 4 times, and then you're doing a standard convolution operation, right? So that is known as a deconvolution operation, in which the resulting output is actually bigger than the input. Yet this doesn't actually happen in our standard neural network. In the standard neural network, convolution neural operation, the output is always smaller than the input, if you guys remember. So that is what essentially is happening. And let's actually come to the specifics once we start writing. All right. So let's start by implementing this model. All right. So let's actually first implement the encoder, and then we'll come to the decoder. Look at these. Look at each one of these steps, right? So there are these 2 blue arrows over here, 2 blue arrows over here, 2 blue arrows. So there is never one single arrow. It's always 2 blue arrows, which means that there are always 2 3x3 convolutions followed by ReLUs together. So let me just consider this as a block in itself, and I'll be first defining that, right? So class base, it's a basic block. So I'm going to name it block. Obviously, since it's related to neural networks, it has to be a child of NN.module, so that we don't have to define like basic stuff like parameter tracking and whatnot. Standard def init self, number of channels that go in, number of channels that come out, right? And whenever you're working with NN.module, very important step. Initialize the NN.module as standard. Now comes the real part, in which we need to define convolution followed by ReLU. All right. Yeah. So I'm going to be doing self.conv1. We go to nn.conv2. Channels, number of out channels is this much, and it's a 3x3 convolution, so kernel size is equal to. So that is there is 1 input channel over here, and there are 64 output channels. And the second convolution is actually 64 to 64, or over here if you see 128 to 120. So number of channels don't change. So let me first define the ReLU as well. And self.conv2 is equal to nn.conv2e. And the input channels is the out channels which is defined. And the output of this is also the out channels. Kernel size, nothing else, right? Whenever we're dealing with NN.modules, we need to define a def forward in order to tell the model how to execute this function. So it's going to take an input as a tensor, And I'm just simply going to be doing return self.relu followed by self.con. Reverse order, by the way. Self.relu self.con of x. So it's first going to do self.con1x. It's going to pass it through a relu. It's again going to do a convolution. And then it's again going to pass it through a relu. So this is this basic block over here that is two blue arrows together. All right, we've done that. Yeah, let's just see if it's working really good. The block is equal to block 1,64, and then I'm going to do. Let me define a random tensor, which is of shape 1,1,572,572, which is by the way defined in the paper. So input is so they said that there is one channel, though our case has 3 channels, so we'll modify it accordingly. And it has 572 by 572 images, and we should ideally get 64 channels and 570 by 570 as the height of it, as given by the paper. And let's say block x dot shape. There is some error. Sorry. Yeah, it works. So I'll just delete it. Define this, and now let me define the entire encoder, right? Because now we have the basic block, and so we just need to put everything together in pieces. So I'm going to define a class known as encoder. Again, going to be an init.module. Def init. Let's see what it's going to take. Let's think about it. So the first argument is always self, of course. I need to define like what all number of channels I need throughout my architecture. So I need to specify that I need 1 followed by 64 followed by 128, 256, 512 until 1024. At 1024 it stops. So channels is equal to let me define a tuple 3, 64, 128, 256, 512 until 1024. It ends over there. Whenever you're using init.module, always do a super.init. Now, I'm going to be defining a list containing all these basic blocks, right? Because there's a block over here, there's a block over here, block over here, block over here, and a block over here. So I'm just going to do self.encoder blocks is equal to nl.module list. Why am I using nl.module list? If you remember last time, we had to explicitly, mention that we had to register each of them as an nl.module child. Yeah. Let me see if I remember. What was this one? Architecture, yeah. Oops. So we used something known as nn.sequential last time, which actually handled all those, registering as child modules of nn.module for us automatically. But if you remember in lab 2, we had to explicitly do that. So go back to that if you don't remember. nn.module list works like this. I mean, the only work of nn.module list is to register each parameter, each of the given inputs as a module child. I'm just going to do that. Block CHS I comma CHS I comma 1. I'm going to be iterating, by the way. For I in range len CHS. What it's essentially going to do is that it's going to create a list of blocks with first input channels as 3 and the output channels as 64. The next one is going to be 64, 128, 128, 256, 256, 512, and 512, 1024. I think I might need to do a -1 as well, because it'll go out of index if I iterate till the end because of this +1 over here. Okay, let's start. And if you look at the paper, after every block, there is also a max pooling layer over here of kernel size 2 by 2. Since this is not a learnable parameter, we don't have to define. I mean, this, and this are not 4 different things. They're all the same thing because there are no learnable parameters in that. So I'm just going to define it once. Pool. Sorry, self.pool. Just a second. It's going to be self.pool is equal to nn.max pool 2D and the size 2. Kernel size is equal to 2. Anyways, we're done with that. Anything with the nn.module. Let me answer a question in the chat box. Srujan says, why is it designed like that? I eat 2 convolutions and ReLUs together. All right. Straightforward answer to that. At that time, and I think even today, people really believe in, very precisely engineering their networks, which should not actually be the case. I mean, because they've specifically chosen, what they've done is that they've specifically designed this architecture by keeping in mind the size of inputs that they had. The problem with that is now that suppose that, let's say that the images that they had is currently 400 by 400, let's say. If I give it 402 by 402, this model is going to fail very bad. That's the problem with these architectures. So the answer to your question is it's just a random hit and trial engineering of networks. Yeah. Which should not ideally be the case. I mean, that's not how AI should be looked at. So that's a good learning point for all of us. But it's easier said than done. It's harder. Easier said than done. I mean, it's very hard to come up with very generalizable architectures. So people just go by and just engineer networks, very precisely. So, I mean, at one point it starts to feel that, it's hard coded in some way because it's not generalizable. But that's a flaw. So, and given that this paper is from 2015, let's give it some slack. That's essentially what it is. But by the way, we're actually going to be designing our architecture such that it's flexible by the given size that there is. Let's go ahead. So, by the way, you can always do 3 convolutions, 4 convolutions, whatever amount you want, right? My purpose over here is to implement this paper very specifically. There is no, so to answer your question, Srujan, there is no reason that you only have to stick with 2 convolutions in a array. Right. So that's that. All right. So a forward which takes in a tensor, and what I'm going to do is that I'm going to actually need the. Okay. So very interesting point. There's this U type of architecture that at one point gives certain number of features that are 1024 features, and it does an opposite of a convolution neural network. But the problem over here is that let's only consider the decoder part, right? Which takes in certain number of features and gives out an image pixel, a pixel map which is of the shape, let's say 388 pixels by 388 pixels, which is given over here. The problem with this is that 1024 features are not enough to produce a map which is as expansive as 388 by 388 pixels. Let's say, what is 388? 388 by 388. It's 150,000 values cannot be derived from 1024 values. There's simply not enough information present in those 1024 features. So what they came up with is something known as a skip connection type of thing, in which basically at every corresponding step, they will basically concatenate information from the corresponding encoder part to the decoder part. So what that will do is that you not only have information from this original features that are deconvolved, but you also have information from the original corresponding encoder part, and that helps the model to retain as much information as possible within its final output. That's how they defined it. Like, it's not a very standard architecture, but again, engineering, good engineering. That's all this paper is. So because now I need to later on add or concatenate values from this, and this, I will have to like store them separately. I cannot simply get rid of these values. Like I cannot simply suffice with this value at the end over here. I will need all these separate values, intermediate values also. So I'm going to be naming them as features, FTRs, and initially it's just going to be a simple list. I'm going to go for block in self.encoder blocks. X is equal to block X. I'm going to do features.append X, and finally X. By the way, the skip connection happens before this max pooling layer, so max pooling needs to be done after you save your features. So X is equal to self.pool. That's it. I'm going to be returning the features. That's what I mean. All right. Let's see if this works. Encoder is equal to encoder. Right. Let's take an input. Let's see what kind of input we had. Same as before, but now because I've defined 3 channels, let's go with 3 channels. Torch.random values of, let's say, 1 image, 3 channels, 572 by 572. So by the way, what would you expect the output to be? And the answer is over here. You would expect the output to be 30 square with 1024 values. That's how this would work. Let's see. Oh, sorry. Wait a minute. Okay, just a second. Right. So first we had a 568 by 568. Then the next should be 280 by 280, which is true, and 128 channels, followed by 256 channels and 136 by 136, which is true, followed by 512 by 512 channels and 64 by 64 as height and width, which is again true, and finally 28 by 28, right, followed by 1024 channels, and that is basically an encoder. So it's working very well. All right, let me just comment it out. Right, we're done with the encoder. Now let's come to the decoder, right, which is actually the most important part of this paper and the most confusing part maybe. So let's start with simple mn.module. Def init self chs is equal to, that's it. So there's 1024 followed by 512 followed by 256 followed by 128 followed by 64. All right, so that's my channel. So 1024 followed by 512 followed by 256 128 64. And all right, let's actually go in where they describe how this architecture is built. So let's first read through the encoder part, and it says the contracting path or the encoder, contracting because you're reducing the number of features. Follows the typical architecture of a convolution neural network. It consists of a repeated application of two 3x3 convolutions, unpadded. We didn't specify any padding, by the way. Each followed by a rectified linear unit and a 2x2 max pooling operation with a stride 2 for downsampling. Downsampling meaning reducing the size. Upsampling means increasing the size. At each downsampling step, we double the number of feature channels as we saw. So 364 become 128, 128, 256, 512, 1024. Now at every step in the expansive path or the decoder, expansive because you're increasing the size of your features. Just a second. Consists of an upsampling of the feature map. So let's first define the upsampling. Actually, before that, let's do some very basic stuff. Initialize the nn.module. Let's save self.chs is equal to chs. All right. So up convolution. What is up convolution? An up convolution is nothing but the opposite of a standard convolution, because a convolution reduces the size of something. Up convolution is nothing but a transpose of a convolution. So it's given by this function known as conv transpose 2D. We're essentially going to be using that. So self.up convolution is equal to, it's nothing but nn.module. So by the way, everything will be defined as you have multiple up convolutions. So it's nothing but nn.2D chs I plus 1, right? And by the way, all right, so let's see what else is needed inside this. Kernel size. Kernel size needs to be 2. It's very standard because you need to first divide it into number of pixels, number of other pixels. I mean, you need to first insert pixels between them, and that is what it's basically asking for. So it's gonna first apply that standard 2x2. By the way, don't get confused by this green thing over here. This green thing is nothing but the convolution layer that exists after that. So this thing at the bottom that you see over here, this is known as transposable convolution. So it's nothing but like it's asking how many pixels you want to insert between any two pixels. Right? So that is what I'm doing over here. So it's going to have a kernel size of 2 and a stride of 2 as well. Like this. So this goes for I range because it's been copied for this plus 1. Now, this up convolution, so upsampling. So right now what we did was we defined upsampling, which followed by something known as an up convolution, which is nothing but a standard convolution, as you'll see in the paper. Let's look at the architecture. So this green represents this up convolution, which we just defined, which is nothing but the transpose of the convolution. It's followed by again that block two 3x3 convolutions followed by ReLUs. Right? So for that, I just need to do, again, the same thing that I defined over here, the same line of code. Except I'm just going to name it decoder blocks because I need to differentiate between that. So meaning that the blocks that belong to the decoder part of the architecture. Yeah, it's basically the same. We're done with it. We're done. Essentially, that's it. Now let's define the. What I mean by we're done, we basically define all the components that are required for this decoder file. And now, whatever actually we're going to be doing, whatever is special, actually comes in the forward part. Like, how do you actually propagate the tensor? So self x. All right. So standard for I in range len self dot chs, which is number of channels -1. First step, up convolution, up sampling. This is this green arrow. So it's nothing but x is equal to self dot up con I. It's given the value x. Now the authors say that it's followed by so let's read it. Consists of an upsampling of the feature map followed by 2x2 convolution that halves the number of feature channels, a concatenation with the corresponding cropped feature map, and two 3x3 convolutions. So my bad, I made a mistake. Let's go back and clarify a concept. nm.conv transpose 2D by default will just insert one pixel between each two pixels, and that is defined by the padding values. Sorry, not padding values. There is a certain value in which you can look for the API. And now on top of that, you can do a standard convolution operation. And the paper specifically mentioned that it should be a 2x2 convolution. Engineering, nothing else. So that is why I've defined this 2x2. Right. And it's a 2x2 convolution, and the paper also mentioned somewhere that there needs to be a stride to when you're doing that. Why? Because you need to half the number of output that you get. So for example, 28. When you upsample it, it first becomes 56, right? But this entire thing is 56 over here, which also contains the concatenation part from the encoder part. So the part which comes from the decoder first needs to be halved using what do you call a stride 2 convolution. So this 28 by 28 first becomes 56 by 56 because of the upsampling. And now I need to do a stride to convolution on top of that. So it will again become 28. And on the 28, I will first add the corresponding part from the encoder part. So 28 plus 28, that will become 56. And that is what this is, 56 over here. 56 becomes 104, 104 becomes whatever number of things. But then you might ask, okay, so let's get that straight first. So I first done an up convolution, followed by encoder. Yeah. So by the way, X will now have half the shape. By the way, 28 first becomes 56, and 56 again becomes 28. All right. Now I need to make sure, like, how do I make sure that this 64 by 64 is converted into a size which is compatible with this over here? Like, how do I make it 28 by 28? So the way to do that is given by them. So they describe it, which says that it needs to be followed by a concatenation with the corresponding cropped feature map from the contracting path. So you need to crop the feature map from the corresponding encoder path to the size in which you require for the decoder path, and so that they both are compatible, and then they can be stuck together. So it's nothing but standard center cropping, basically. So encoder features are going to be self dot crop. I didn't define self dot crop. Give me a problem. Oh no, let me define it later on then. Self dot crop. Let me define. I'm going to be defining self dot crop. Self. I'm going to take encoder features themselves. That's also going to take X, which is the input that needs to be passed. Right. So takes an encoder. Features. And the ith value of it, because we're dealing with the corresponding ith from the decoder will be the ith from the encoder as well. So that's it will become clear in a minute. And X, right? So let me just define this crop function over here. Oh, where does this encoder features come from? I need to specifically pass it to this forward value. That's what it comes. What I need to do is that I need to do a center crop on the what do you call on my encoder value based on and what will be the size of the crop value? It will be whatever size I need from the decoder part, right? So the X is nothing but the decoder value. It's a decoder activation, decoder X. The X that comes from the decoder. Whatever shape that X will have, I need to crop my encoder values the same as that so that they can be concatenated together. I'm just going to take the height and the width of X. I don't need the number of channels. I don't need the number of images in the batch. And encoder features is going to be nothing but dot vision, transforms, dot center crop. And I'm going to tell it like what size I needed for the encoder crop, and I'm just going to pass it to encoder features. That's it. Simply return these encoder features. We will see if it works or not. So now these encoder features will have the same shape, which means that even though my input encoder feature will have 64 by 64 channel, I'm going to do a center crop of 28 by 28 so that 28 and 28 can be mixed together, and now I will have 56, 56 as 54, 56, 56 as the output. We'll see if this works. Let's see. I'm done with that. This is followed by a standard 2 convolution neural network blocks. So, oh, sorry, first I need to concatenate these two, right? So X is equal to torch.cat, which is concatenate of X and the encoder features themselves. It makes sense, right? And I need to make sure that it's done across height and width, and it's not done across the number of channels. So which is why I need to specify that the dimension across which this needs to be concatenated is 1, not 0. 0 is the channel part. Sorry, no. 0 will be number of channels. Number 1 will be height or the width, right? And across any one of those dimensions, you need to concatenate whatever is common. So that is that. That is how you think that dimension 1 is the dimension across which the concatenation is to. Take a look at this paper, read it very carefully at the end of it, and you'll see exactly what I mean by that. So concatenation is done, followed by a standard decoding, standard 2 convolutional layers with those blue arrows basically. So that's defined in my self.decoder blocks, I think. Decoder blocks. I and parts and X. We're just going to do a return X. I think this is the architecture. Sorry. F curve. Unexpected indent. Okay, my bad. Let's see if it works. So decoder is equal to decoder, right? Let's say X is equal to torch dot random values. We'll have 1,1024 channels, right? And the input will be 28 by 28. Look at the architecture. It says very clear. So let's do 28 by 28. Let's do let's do a forward pass. Put an X, and it also needs the encoder feature separately, so that was stored in these FTRS over here. So let me just pass it FTRS. But I think FTRS. Let's try it as is. Let's see what happens. I think this is going to give me an error, but just so that you guys understand it as well. Let's see. Yeah, given groups is equal to 1, weights of size 51210 is expected 1, 576, 56, 56. We have 1024 channels, but with 576 channels instead. The problem that essentially we're having right now is that let's see FTR is shape. It's a list. So the first thing that I need to do is let's see what's happening. We did print out the shapes. So the first will have 568 by 568, 280 by 280. And oh, so you see how so by the way, encoder blocks is it comes from top to down, so from left to right, for example, essentially. Decoder also goes from left to right. But now, if you want to do, if you want to index them using the same I, so decoder blocks I, and we want to correspond it to the up convolution network I, you need to reverse one of them. So I'm going to first have to reverse this encoder list over here, and I'm going to do simply by colon minus 1. So it basically reverses a list. And now I don't want to count my 1024 list because because it's not going to correspond to any transpose, any skip connection. So I'm just going to skip that, and now hopefully that works. So that is why the error was coming that 1024 is not compatible. I'm expecting a 5. Yeah, this works. So let's see. Final output is supposed to be 388 by 388. And that is essentially around 64 channels, 388 by 388. And now the paper finally says that finally, at the final layer, there's a one-by-one convolution which is used to map each 64 component feature value to the design number of classes, which in our case is 2. Right? So we'll do that later on. Anyways, the decoder works. I'm not gonna touch it. Yeah, I'm just gonna comment it out. Done with our decoder. Now let's build a unit architecture, which is nothing but compiling encoder, decoder, and that final one-by-one combination. So I'm going to do a class. This again will be an input module. Self encoder channels is equal to say I'm just going to copy paste. Decoder channels. Again, copy paste. What else do I need? Think about it. Number of output channels, of course. In this case, you might think that it's a binary classification, so you might need two output neurons, but that's not true. Whenever you have binary classification problem, you only need one output, because that's going to be either 0 or 1. So, num classes is equal to 1. And I'm going to be needing two other things, which I'll explain in a bit. But let's go. All right, so I'll just explain it anyways. The input was of the shape 400,4. Sorry. In this case, the input was of the shape 572 by 572. Right? 572 by 572. But the output is of shape 388 by 388. Now, these two are not compatible. I mean, these masks cannot be interpolated. So this is one of the drawbacks of the architecture, and they could not essentially, engineer this really well. And so what you need to do is that, since anyways, on one hand, you're cropping images from the encoder part, so you should be able to have the liberty to do the opposite of that, which is nothing but interpolate the values from 388 to 512 or 570, whatever number is required. So I'm gonna do that. So output size should also be mentioned, by the way. Output size is equal to, and by default I'm going to give it 400 by 400. Standard, as before, you should always initialize the NR module. So it's super init. All right, self dot encoder is equal to encoder channels. Self dot decoder is equal to decode number of channels. There needs to be a one-by-one convolution that exists from the final layer to the number of channels that you want. So I'm going to name it head. It's called the head of the architecture. Self.head is equal to nn.con. It's a 2x2 convolution layer. nn.con2d. It goes for decode channels. The final number of channels which exists within the decode number of channels, which is 64 in our case. Followed by num classes, which is going to be 1, and it's a one-by-one convolution, so kernel size is 1, right? That's that. And self dot out size is equal to All right, def forward, self, comma x, encoder features, because I need to first store the encoder features in order to use it for a decode for the decoder part. So it's nothing but self dot encoder x. Out is equal to self dot decoder encoder sorry encoder features, because that's going to be the input. So the input of the decoder is the output of the encoder, if you remember. So I'll need to do that again. -1 maybe. -1 meaning the last element of that, and of course the entire feature list itself, but reversed, and then excluding the 1024, excluding the first part of it. So that's right. That is decoder. And once you've done with that, let's do something else. Yeah, once we're done with that, we need to pass it through the head. So self.head out, and that's going to give us the answer, right? By the way, before that, we also need to interpolate it to the final value that we need. So that's going to be out is equal to, I need to interpolate it, right? So let's see what exists in torch.nn, torch.nn interpolate. It exists in a library known as torch.nn.functional, and it's a very standard practice to import it as F, as the letter F. So import torch.nn.functional as F. And let's look at the syntax. Yeah. Downs or up the samples to input given either the output size or the scale factor. Right. So it's F dot interpolate out to the given size, to self dot out size. And I'm just going to go return out. Let's see if it works. Unit is equal to unit. Yeah, standard stuff. Dot CUDA. So because we're going to be using the GPU now. Let's see if this works. So x comma y is equal to next iter trained here. So by the way, you remember I was telling that models. So I mean, because they're so specifically engineered, they cannot be. I mean, even if you slightly change the output, the input, the output is going to change dramatically. But now because we've used an interpolation which is adaptive on its own nature, so now we can pass in any output size, and we can expect the output to also be of the same of the same size. All right. So x is equal to x dot CUDA, because there are two things that you need to take care in PyTorch. First, the input, the x's and the y's should be on the GPU, and the model should on the GPU. So that's how you put the entire model on the GPU. Let's do unit x dot shape. So initialization is going on. Let's see. Yeah, so 8 channels, 1 output channel, which is the mask, and 400 by 400. So it's working perfectly. So we've now implemented this entire paper from scratch. It's a good exercise for you guys, because now you're going to have a research component in this course as well. So this is how you read a paper and you implement a paper from scratch. So that's how you implement papers, by the way. All right. Model is done. Now let us do some other stuff. So model is done, data is done. We need to train our architecture. So before that, we need the optimizer. So I'm just going to copy paste the code from last time. right? Done with the optimizer and the learner as well. There is this deep learner, but I need to do some changes over here. Let's see. Self.model, but model dot to device, whatever device we have. Optimizer, self.model dot parameters. Cool. Okay. I have a calculate grad. I don't have any pre-processing now, so I'm going to be doing this. No pre-processing. Just a second. Yeah, no pre-processing. I don't need accuracy either. So accuracy is not the best way to go about it. I'll tell you why. But so yeah, optimizer is done. Yeah. To track the progress, I'm going to be using a library known as DQDL, which you'll see is quite useful in a few moments. And I'm just going to go for XY in DQDM. So DQDM basically goes on top of any iterator. And I'm going to do over here. Oh, I don't need it over here. So what's the loss function, by the way? Loss, we'll talk about the loss function. What should we print? By the way, accuracy is not a really good measure for segmentation tasks because, I mean, even if a very less amount of wrong pixels that you calculate, you might the architecture goes completely haywire. I mean, the accuracies goes way bad. I mean, you might think that the model is not working, but it's actually not that the case. I mean, it usually works fine. Loss is actually a good way to identify. The lower the loss, the model is working properly. I'm going to be printing the loss, by the way. And for that, I'm going to be storing my loss in a list. So loss. Sorry. I need to initialize it over here. So self.loss. Self.plain losses. This loss is equal to self.calgrad. And I'm just going to go, sorry. Yeah. Self.plain losses. Blend loss. That's that. I don't need accuracy. I'm going to remove accuracy. So over here as well, I'm going to have self.loss. So self.loss, self.validation losses is equal to self. Oh, sorry. One more thing that needs to be done. This is the validation set, and because of that, Uh, if you remember that the loss function, whenever you calculate the loss function, it should not be counted within the computational graph. So you need to do something known as that with torch.nograd whenever you're doing any sort of loss operation in the validation set. So with torch.nograd, uh, loss is equal to this is, and I'm just going to simply return the loss. And I'm going to go that yeah, so I have losses over here, and I just need to return the average of that loss for across all values. So it's just simply sum of loss divided by len of loss. Uh, just for the sake of clarity, this is val losses. Val. All right. We're done with this. I'm after every epoch, I'm just gonna go epoch in loss. I'm just gonna go sum of train losses divided by mean. Oh, sorry, length of train losses. That's the average of all the train losses. And yeah, I'm gonna have to do that. So uh, train loss and valid loss is equal to self dot validate epoch. Okay, loss function. What is the loss function, by the way? Uh, the so the loss function over here is slightly different. If you think about it, that the one output neuron that we got is essentially nothing but a continuous value. It will give a continuous value, but we want it to be either zeros or ones. So for which we'll have to use that kind of sigmoid approach that we used in the logistic regression case. So first we need to apply a logistic regression followed by a standard binary classification loss. So that is already defined in PyTorch in something known as BCE with Logit's loss. Logit is nothing but another name for sigmoid function. So and BCE stands for binary cross entropy loss. So you first apply the logit function followed by the BCE function. So that's essentially the loss function that we're going to use. Loss function is equal to nn dot BCE with logit's loss. Just I think it's going to give me some error, but let's see. Sorry, it is from TQPM. A model is not defined. All right. Unit. Optimizer is equal to. Okay, so let me. Before that, let's do something. Let's see if this works, by the way. By the way, this is your unit architecture, and it all works well. There's an encoder, takes in 3 channels, and finally gives out 1 channel as the output. Model. I hope. Let's see if this works now. Okay. One more thing. X's and Y's also need to be put within the GPU, right? So X batch, Y batch equal to X batch, Y batch, X batch to Y's. I think they should work. And Y batch to Y's. Similarly, I need to do it for the validation case as well. So let me do it beforehand itself so that it doesn't give me a problem later on. Y dot to Y's. So yeah, your unit architecture is now training, and you guys can see how your model is performing after that. Your loss should come somewhere in points, so less than 1, 0.4, 0.3 as such. And what you can do as a task, you can train it for longer and see how it performs. So see how the model performs by actually passing it an input portrait and seeing like what kind of mask it is creating. So with that, you're done with segmentation models. And yeah, it is as simple as that. So let's recap what we did today. We first looked at what segmentation it is a problem. We built a segmentation data set. We implemented the original unit architecture, which is a standard segmentation model from scratch, everything from scratch using nothing other than PyTorch itself. And we trained the model using whatever API we had already created. With this, we're done with segmentation models.